This morning in North Carolina, wheels are spinning. Determination is winning. A passion is now a thriving business, and it shows no signs of slowing down. How? The power of a conversation, like the one Clint Spiegel had with First Horizon Bank about starting a bike wheel manufacturing facility in Asheville. Now it's not just talk, it's rubber meets road. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint. First Horizon Bank, member FDIC. Recently, our client Tommy met his banker to discuss continuing his father's restaurant legacy. In us, he found a partner that understood the importance of passing the torch. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on the Space Nuts podcast, episode 238. I'm your host, Andrew Dunkley, and with me as always is our expert astronomer, Professor Fred Watson, astronomer at large, in fact, because he's got a large brain with a lot of information in it to share with us today, unlike every other episode. Hello, Fred.
Hi, Andrew. 238 is a good number. It's approximately my age.
In dog years.
Dog years, that's right.
Maybe.
Yeah.
Maybe.
They're all good.
That's good. I hope you're well. Everything good?
Yeah, all well, thank you. Still alive. That's
pleased to hear it.
Yes.
Yes, indeed.
That's
today we're going to be talking. Sorry.
It's all right. It's a joke that nobody will understand if they're not seeing this on the YouTube. But as I look at your image on the screen and mine, our respective ceiling fans are both at exactly the same angle.
They are too, aren't they?
Who says this is not a bond made in heaven when your ceiling fans are at the same angle? Anyway, anybody who's not seeing this on a screen, just ignore that. Sorry about that.
So bonus material for YouTube viewers. That's what that is.
Okay.
Now, down to business. Yeah. Today, we will be probing the Martian atmosphere at a time when it was warm and wet, which is impossible, but possible. Apparently, we'll be talking about that. We're going to focus on Mars today because they want to get there faster. It's a bit of a slow trip. It's kind of like driving a houseboat up the Murray River at the moment to get to Mars. But they want to get there faster, and nuclear power could be the answer. And speaking of answers, we're going to get questions from Aaron in Nebraska and Pete in Sheffield today. Before we get onto our topics, Fred, what sort of prompted you to want to talk about Mars so much in this episode?
Well, look, Mars is going to be the big news this month, February 2021, with 3 spacecraft arriving there around about the middle of the month. If I remember rightly, it's the 18th that is the scheduled date for Perseverance's 7 minutes of hell as it enters the Martian atmosphere and makes its soft landing, we hope. And I think the Chinese spacecraft Tianwen-1 is due about the same time, and hope the UAE mission will go into orbit, I think, around Mars about the middle of the month too. So you and I will have plenty to talk about, but I thought we might just set the scene with the red planet,
yes,
which is the focus of this week's recording.
And of course, Mars is a cold, dank, dry, desolate place. Effectively, we're certainly unlocking a lot of its secrets, but it never used to be that way. What was Mars like before its atmosphere was kind of, unable to hold its integrity? I think that would be the best way to describe it.
Yeah, the most highly supported view is that there was a time in Mars's distant past, probably 3.8 to 4 billion years ago, when its atmosphere was essentially warm and wet, very like the Earth's atmosphere, with an average temperature of about 15 degrees Celsius over the whole planet, with plenty of moisture in the air and on the ground, because the overwhelming evidence is that Mars had river flows, it had lakes, it had seas probably. The northern hemisphere is very flat and very smooth, which suggests that there was a large body of water there sometime in the past. The only thing that's changed that view in recent months, and you and I have spoken about this, is the idea that maybe Mars, some of these water features could have been formed underneath huge glaciers, so that you've got this, sort of almost like snowball Mars, but with the rivers made of meltwater effectively flowing underneath these glacial sheets. So that's a slightly new idea. It's got some support, but I think the overwhelming view is still that at some time, even if it might have been only for brief periods, Mars had a warm and wet climate. The trouble is, how do you probe back into Mars's climate? And that's where the story begins. Because there is
have they been able to do so, or are they looking at ways of doing so?
Yeah, it's a future possibility, but one that's really intriguing, and with good reason to believe that this will be a very successful venture when it finally gets going. So we know from a spacecraft that's already in orbit around Mars, it's called MAVEN or MAVEN. Somewhere I've got the acronym, which is Mars Atmosphere and Volatile Evolution. There you are. You've got to stick the N on the end from evolution. But Mars Atmosphere and Volatile Evolution, what it means is it's sensing the upper atmosphere of Mars. It's been there for 6 years, actually, collecting data. But one of the things that MAVEN has uncovered is that there is a flow of actually charged particles from, in other words, what we call ions in science, IONS, which are particles that have lost some of their electrons. And these particles of oxygen, carbon, nitrogen, argon, these have been coming off the surface of Mars for billions of years, and MAVEN has detected them. I've seen results from those detections, which are really interesting. But what's new, and this is the work that we're talking about today. It's actually come from University of California, Berkeley, and other institutions. What's new is the recognition that those ions, those charged particles, have found their way not just into space, but also onto the surface of Mars's largest moon, or larger moon, there are only two, which is Phobos. Phobos, an object 30, 40 kilometres across. Really interesting in its own right, because it's got a very low density. It's probably something a bit like pumice in its makeup, and space scientists are not that sure where it came from and how it got to be like it is. But the bottom line is that Phobos is in the flow of these ions, and they will essentially deposit on the surface of Phobos, which is not subject to any other kind of phenomena apart from radiation from the sun, which is well understood and you can deal with that. So the suggestion that has been made is that if a future spacecraft could go to Phobos and collect samples from its surface and then bring them back, they might tell us not only about the origin of Phobos, but the material that's come from Mars, particularly if, and this is the crux of the mission, if you landed the spacecraft on the side of Phobos that always faces Mars, because Phobos is like the moon. It always has the same face.
Tidally locked.
Planet. It's tidally locked, exactly. In fact, it's even more tidally locked than the moon, because Phobos is actually 60 times closer to Mars than the moon is to the Earth. It's very, very close. It actually whizzes round. One of the curious things about Phobos is its orbital period is so short, and I can't remember, it's a matter of hours, but it's so short that Phobos rises in the west and sets in the east, which must be quite entertaining to watch. Most other things do things the other way around. Anyway, if you send a space probe to land on the Mars-facing side of Phobos and bring back samples, it is just possible that what you might get is a timeline history of the atmosphere of Mars, which might tell us what the atmosphere was like in these ages ago, these times, 3.8 or 4 billion years ago, when Mars is thought to have been warm and wet. Now, the good news to this story is that there is already a spacecraft planned to do that. Which
I was going to ask you.
Yeah. JAXA, the Japan Aerospace Exploration Agency, they have something called MMX. MMX is a kind of acronym for Martian Moons Exploration, and it's a probe that's going to Phobos, and the intention is that it will collect samples from its surface and bring them back to Earth. The Japanese are very good at that. They've done it twice with asteroid samples. We've seen the most recent one landing in Australia at the end of 2020 from the Hayabusa 2 spacecraft. So it's a mission with a high chance of success. And would be very, very interesting. It would be brilliant if we could just sort of open a book, an archive of the past atmosphere of Mars that says, yes, back in 3.8 billion years before the Common Era, Mars had this climate, this particular level of carbon dioxide in the atmosphere. That's basically what you're looking for, because that would be what kept Mars warm. So, it's a fantastic, it's a fantastic possibility, and hope you and I'll talk about it in 2024.
Oh, I hope so too. I suppose what mystifies me to a certain degree is how it was that Mars was able to maintain for some period of time a wet, warm environment. Yeah. And then it couldn't. I mean, what changed, or was it just, it was always destined to fail?
It was, because it's too small to hold on to a thick atmosphere. So there's actually another aspect to it as well, and that's that it doesn't have a magnetic field. But these are the two factors. They come about because Mars is small. It's smaller than the Earth by a factor of 2, so its diameter is half the diameter of the Earth. That means its core would have cooled much more rapidly than the Earth's core has done. That means that there would be no chance of supporting plate tectonics, which is one of the crucial things that stabilizes our atmosphere, in fact, and it would have stabilized Mars's atmosphere. Plate tectonics are driven by internal heat. There is some evidence from sort of residual magnetic fields on Mars here and there that look as though they might have been formed around the boundaries of plates, of continental plates. But they must have solidified, a very, very long time ago, because we believe that Mars's crust is now sort of continuous, like an orange peel. And we believe it's been like that for a long time, because that's the explanation as to how Mars's volcanoes grew so big. In particular, Olympus Mons, the biggest volcano in the solar system. It's because there was no plate tectonics shuffling it around over the mantle hotspot that was driving it. As the Hawaiian Islands have done. They've moved around above the hotspot, so you've got this chain of islands. There's still, Mauna Kea is still, the biggest mountain in the world when you reckon it from the sea floor.
Yes, exactly.
But it's nothing like Olympus Mons, and Olympus Mons is thought to have got to that size because there is no plate tectonics. So plate tectonics is one of the things that stabilizes the carbon in an atmosphere, and if you get rid of that, then you've got this risk of losing the atmosphere to space, plus the fact that, as I said, Mars does not have a magnetic field, so it doesn't have a magnetosphere protecting it from the radiation of the sun, and that too is a driver for the evaporation of an atmosphere. So it probably lost its warm, wet atmosphere quite early on in the piece. But the trick is to go to Mars with MMX and find out. Maybe we will. Yeah.
So it would have developed that warm, wet atmosphere while it had a continental tectonics and a warm interior. But as that cooled off and everything sort of set in stone, literally, it was doomed.
Yeah. It's doomed. That's right. Yes.
Very sad.
Why, but, that's one reason why the idea of terraforming Mars is a non-starter, because Mars is not big enough to hold on to an Earth-like atmosphere.
Fair point. You'll just have to live in bubbles.
Bubbles, yes.
I suppose.
Which I'm sure we will. We're good at bubbles.
Yes, indeed. I've seen some marvellous theories, mainly in science fiction books, about how we could live on different planets in our solar system. Bubbles is a very common one. One I read about, and it was Kim Stanley Robinson, living on Mercury. They basically had the city built on a railway track, and the railway system worked by the sun superheating the line, and the expansion pushed the city just beyond the crest of the planet, so it was always in shadow
on the
and
dark
not
side.
overheating. And it just went around and around like that. Very clever.
Yeah.
But, disaster could easily happen if you came off the rail or something. But yes, fascinating. And yes, let's hope we do get some answers and are able to talk about them in a future episode of Space Nuts. And that's what you're watching and listening to right now. Space Nuts episode 238 with Andrew Dunkley and Professor Fred Watson.
A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC.
This episode of Space Nuts is brought to you by LastPass, simplifying your online life. Now, if you're anything like me, you probably find one of your biggest frustrations in life is remembering all your passwords, all those login details, usernames, passwords, important information that have built up over many, many years. And you might have hundreds of them. I know last time I counted, I had like 88 passwords for various things, and it can get quite cumbersome. So what can you do about it? Well, I use LastPass. It's a password manager. It's a fabulous solution to this problem. And believe me, the relief is unbelievable, not to mention time-saving. Now, you can sign up for LastPass and you'll be joining 25.6 million fellow users from around the world and 70,000 plus businesses. With those kinds of numbers, they've got to be doing something right, and they do. In my experience, it has simplified everything. I've got every username, every password from everything I do built into LastPass, and it's integrated. I can use it on my desktop, I can use it on my laptop, I can use it on my phone, I can use it on my iPad. It's that simple. And it can even work in a way whereby you don't have to type in anything. You open LastPass, you type in what you're looking for, let's say it's your Gmail account or something, and it will bring it up and you just click on the link and it will open it for you. You don't have to do anything. It is really, really good. Now, you can get the premium package for around $4.50 a month, and there's a family and enterprise plan as well, and it works, as I said, across all devices. Put your passwords in, you can go into autopilot, you can reduce the stress. It's really fabulous. I highly recommend it, and it will give you peace of mind. You will never have to sit there going, oh no, I've forgotten my password. It's one of the worst feelings in the world, and this is the solution. It's really simple and highly secure. I mean, it is very safe. All you have to remember is a master password, one password, so that you don't have to remember any of the others. So check it out. Go to spacenutspodcast.com/LastPass and help support the show. Sign up and you can check it out for free at spacenutspodcast.com/LastPass and just simplify your life. Link details are in the show notes and on our website. Now, back to Space Nuts.
3, 2, 1.
Space Nuts.
Welcome back. This is the Space Nuts podcast. Andrew Dunkley here, Fred Watson there, I think.
Indeed.
If you want to support the Space Nuts podcast, there are several ways of doing that. One is to sign up as a patron. And as I've mentioned over the last couple of weeks, we'd really like to make the entire podcast ad-free down the track, and that can only happen with the support of patrons. So if you would like to do that, you can do so by going to our website, spacenutspodcast.com. Click on the little button at the top right called Support Space Nuts, and you've got options to join Patreon or Supercast or make one-off donations through PayPal. It's completely optional, but it is a way of keeping the podcast alive, and we're ultimately aiming to get 1,000 patrons if we can, and make the thing self-funding through the listening audience, which I think would be wonderful. And thank you to all of those people who have already signed up. It is a wonderful thing, and it's not going to cost you an arm and a leg, unless your arm is worth $3. That could be a problem. But yes, if you'd like to look into that, just go to our website and click on the Support Space Nuts link and find out how to do it there. Now, Fred, still on the subject of Mars, we've dedicated a fair chunk of this episode to my favourite rocky planet. And they now want to get to Mars faster. Now, it is depending on when you go and how you fuel it up. It's a long journey. It is a very, very long journey, sometimes longer than it should be, I suppose, but you've got to allow for so many factors when you're travelling across the expanse of space, or just going to the next door neighbour's place, as is the case with Mars. But they're wanting to get there faster, which makes perfect sense. And the answer might be nuclear rockets.
Yeah, that's right.
I like this idea, I really do like this idea.
Yeah. It's not a new one either. It goes back to the 60s, the earliest days of rocket flight. People were talking about using nuclear rockets to whiz around space. In fact, we were thinking of doing everything by nuclear power in those days. But just talking about Mars, the standard journey time for Mars, as we've seen with the spacecraft that are currently on their way there, they were launched in July last year. They will arrive in February this year, so that's a 7-month trip. And that's actually about as quickly as you can do it with normal chemical rockets, because what you're doing is you're looking for the lowest energy transfer between the orbit of the Earth and the orbit of Mars, and that is something called a Hohmann transfer orbit. Hohmann, if I remember rightly, is his name. I checked up the guy a while ago. He's an engineer, but he was, I think, in the 50s proposed the way to get from one planet to another was to essentially put your spacecraft into an orbit around the sun, which is elliptical. It's basically a stretched orbit, not circular, but one that's quite elongated. You put your spacecraft into that orbit. It heads halfway around one orbit, and then you basically fire your braking rocket so that it goes into orbit around the other body, which is Mars. And that's the thing that gives us the standard 7-month or so travel time. 7 to 8 months, sometimes 9 months, depends on the exact orientation of Mars and the Earth. But the other point about that is you can only do it every 2 years, which is why we had this rush of spacecraft being launched last July. Because if you miss your window, you send your rocket off in its transfer orbit, and when it gets to the orbit of Mars, Mars is already somewhere else. It's moved along. So the timing has got to be perfect, and that is why you've got this 2-year window. It would be very good to be able to change all that. And that's why people are once again starting to look at nuclear rockets. There have been many nuclear rockets tested, in fact, never, I think, going into space, but certainly tested on the ground, dating through the late 1960s. Plenty about this stuff on the web. But the program, kind of in the post-Apollo era, was shut down. In fact, in 1973, in the United States. I know nuclear rocket technology has been tested in Russia, we know that, but not in the United States. It was shut down in 1973 with basically the dawn of the Space Shuttle program, when the idea of going to Mars was shelved. Because the US wanted to build a space station and wanted to have a reusable spacecraft, the Space Shuttle, which that then basically took over. well, let me just take a pause there. Nuclear rocket research stopped in 1973, but nuclear research didn't. And we now know much more about nuclear technology than we did back in the 1960s. And in fact, there is a difference in the kind of fuel that you might use. It was always highly enriched uranium that was proposed back in the 60s, which is kind of the stuff that you make nuclear weapons out of. It's not very nice, but there is something. Yeah, good stuff. Yeah, there is low enriched uranium, which might now open the way because the technology has moved on. Basically, what you're trying to do, just let me explain how a nuclear rocket works. You get your radioisotope.
Aside from going kaboom.
Yeah, kaboom. Yeah, it shouldn't do that. It's gone wrong if it does that, and you're in bad shape. It's basically a pellet of uranium that is undergoing fission, which is the process that breaks up the atoms and releases heat. And the amount of heat that is released is enormous. And what you do is heat up a gas, it's usually hydrogen, up to about 2,500 degrees Celsius. And then you blow that out through a venturi at the back, which gives it a very high velocity. And the key point about that is you end up with 2 to 3 times the efficiency, the propulsion efficiency of a chemical rocket, one that uses liquid fuels, the standard thing. So you've got this sudden increase in efficiency by a factor of 2, and that means, for the same size of rocket, you get 2 or 3 times more power and more of the oomph. So there is a proposal now. This is it's actually mandated by the US Congress, which approved $125 million for this project on the 22nd of May 2 years ago, 2019, to look at the development of nuclear thermal propulsion. And I'm not sure, NASA is the agency that's looking after this. That the approval, and I'm quoting here, calls upon NASA to develop a multi-year plan that enables a nuclear thermal propulsion demonstration, including the timeline associated with the space demonstration and a description of future missions and propulsion and power systems enabled by this capability. It's a really broad remit. It's it's saying, okay, we'll give you nuclear toys to play with. What can you do with them? So it's very interesting prospect.
Yes, indeed. So, they're more powerful, therefore faster. So how much quicker would the trip to Mars be with a nuclear-powered rocket?
Well, even just the standard thing that we've been talking about, using nuclear fission, using uranium as a fuel, the prospect will bring the transfer time down to 100 days, which is kind of 3 months-ish. So you're cutting it by more than a factor of 2. Just because you can actually boost the spacecraft to a higher velocity, that puts it into a more tightly elongated orbit, and you get there quicker. There is another advantage. Actually, there are a number of advantages. One is that the lower travel time means that you don't need, anything like the same amount of, supplies, the resources that the astronauts themselves use during the flight. And paradoxically, even though you're being driven by a nuclear rocket, you've got a lower radiation dose from the solar radiation on the astronauts as they fly to the moon. So it's kind of got advantages on both sides. And a third one, which I think is in some ways, the clincher is this. It means that you're not limited so strictly to this 2-year window. You could take yourself off to Mars over a wider window of opportunity, if I can put it that way, because you've got the possibility of additional thrust, that you could actually choose your departure time, probably not completely freely. You probably still have windows, but they would be much wider windows than they are now. You don't have to rely on the two planets being exactly aligned.
That's good news. And so are you confident that this will happen? I mean, when you use the word nuclear, it sets off alarm bells.
It does,
for reasons of, dating back to the Second World War, nuclear explosions. And the Cold War and all the nuclear warheads that were littered all over the countryside that basically scared us out of our wits when I was a kid.
Me too.
So when you use the word, you automatically think of the terrifying aspect of nuclear power. But essentially, it's actually very clean energy, and it's very efficient energy, and a lot of countries, unlike Australia, use nuclear energy to power the homes and businesses of their people. So it stands to reason that it's a logical step to take in launching rockets. Is it? I'm assuming it's a fairly safe way to go.
Yes, it would not be done if it wasn't safe. And just to reiterate what you've been saying, I mean, I think the main reason why nuclear got such a bad name is 3 Mile Island and Chernobyl. Those accidents were because the world's still littered with nuclear weapons. It's crazy, but hopefully there will be times when that tension is eliminated. I can't wait for that. The nuclear power industry suffered enormous consequences from those two big accidents. But on the other hand, nuclear power is used routinely in space travel because, Perseverance on its way to Mars at the moment has got an RTG, a radioisotope thermoelectric generator on board, which is basically a bucket of plutonium, which decays and generates heat and hence generates power. So I've got
a bucket of plutonium right here, actually. Yeah, it's a specially ventilated receptacle that I keep it in.
Yeah, Don't lick it or anything, Andrew. Just don't taste it or anything like that, because
no,
it goes wrong, does that? But just to wrap this up, though, people are also looking, of course, as the whole power industry is, at nuclear fusion, which is the process that powers the sun, and that is a much more efficient nuclear process than fission. Than using uranium, and it's actually much safer as well. That's why there's all this research that's been going on again since the 1970s on how you can build a nuclear fusion power plant. And I've visited an engineer in France who works on ITER. ITER is the European nuclear fusion experiment. It's an enormous experiment. It's been going for years. Huge amounts of money have gone into it, and eventually it will sustain fusion energy. I think there are experiments in China too of a similar kind, and probably Russia as well. But the point is that once you can master the trick of keeping a fusion reactor going, then you've got almost limitless power with a huge amount, huge advantages in terms of power to weight, which is one of the things that interests you as a space engineer. You get enormous acceleration for the amount of mass that you're carrying. So there is a group, excuse me, there's a research group in Princeton, the Princeton Plasma Physics Laboratory. They're working on a concept called the direct fusion drive, which is a fusion reactor for space. It was originally developed in the early 2000s. Excuse me, uses a hot plasma of helium-3 and deuterium in this magnetic container, and essentially you get nuclear fusion from that, and that heats the propellant then to these very high temperatures, and sends it out. It's also got a magnetic component. This has a linear magnet accelerator. Really interesting technology, which would be wonderful if it came good, and then we would be zapping off to, what do they suggest? You could get to to Saturn in 2 years. As against the 10 years it takes now, and about Pluto in about 4 years. So really quite extraordinary.
Indeed.
Yeah, looking to the future.
Yeah, it's very exciting. I'm sure they'll crack all these problems, and once they've developed sublight engines, we can get to Mars in an hour. And then when we've developed warp technology, we'll just take a couple of minutes.
It will, yes. In fact, it could be instantaneous.
Yes,
but you never come back. That's the problem.
Yeah. All right. We'll watch this space with interest, because it sounds like things are really ramping up in terms of the power needed to get around. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Space Nuts.
This is the Space Nuts podcast, episode 238, with Professor Fred Watson and myself, Andrew Dunkley. I talked about our website earlier. I have not mentioned for some time the Space Nuts shop, which you will find on spacenutspodcast.com. If you click on the tab that says shop, you can go in there, and if you click on catalogue, you can see everything. We've got bubble-free stickers. We've got dad hats. I'm still trying to define a dad hat, but I think it's just a cap with a logo on it. And there's embroidered T-shirts. There's embroidered polo shirts for men and women. You've got the matte black magic cup. I think when you put a ball in it, it disappears. I don't know. But there's also the stock standard coffee mug and all sorts of other things. The hoodie, if you want to go around, at night scaring people. We've got a hoodie and the unisex T-shirts. They're all there in the Space Nuts shop, which you'll find on our website, spacenutspodcast.com. Check it out, especially if you've got someone who's hard to buy for. This might just be up their alley, especially if they're astronomy buffs. Could be well worth it. And not overly expensive either. That's terrific. Now, Fred, we have some questions to answer, and our first question today comes from Aaron, and he's in Nebraska in the United States.
Good afternoon, Andrew and Professor Fred. My name's Aaron Inkstrom from Lincoln, Nebraska, and I'm a longtime listener. I had a question about the speed of light. If the speed of light in a vacuum is considered to be the speed limit of the universe at approximately 300,000 meters per second, then does that mean when the universe was much smaller and compact that the speed of light, or the speed limit of light, was much slower? Given that a vacuum is space devoid of matter, does that also mean that the speed of light will increase as the universe expands? Thanks, and I look forward to your insightful answer.
The speed of light is something we've talked about before. I think we actually talked about it in last week's episode to a certain degree. But yes, the question is certainly one that prompts a lot of interest from people from time to time. If the speed of light in a vacuum is considered to be the speed limit of the universe at approximately 300,000 meters per second, does that mean when the universe was much smaller and compact, the speed of light was slower, and as it expands, will it get faster? I think that's the gist of it.
It is. And let's just set the record straight. The speed of light is 300,000 kilometres per second, not metres per second.
Kilometres per second.
Yeah.
Right.
So it's extremely fast, 300,000 kilometres per second. And look, this is a great question, Andrew. I'm glad that Aaron's posted it, because it raises things that are absolutely fundamental in the world of cosmology and astrophysics. And it goes back to the late 19th century, our understanding of all this, to two scientists, and I can't remember their first names, but they were called Michelson and Morley. They're probably both Williams or something like that. It's a very common name at that time. In the 1880s, they performed an experiment that essentially demonstrated that the speed that light is not kind of traveling through anything in the same way that sound travels. With sound, it's being carried by a medium, which is the atmosphere in normal use. In space, there was this theory that space was filled with something called the ether, and that the ether was the medium within which light travelled. And if that's the case, then you should be able to detect the ether by looking at the way the speed of light varies depending on which way the Earth is facing. So as the Earth goes around the Sun in its orbit, on one side of the orbit it's going at 30 kilometres per second in one direction. On the other side of the orbit, it's going at 30 kilometres per second in exactly the opposite direction. And that is a big enough difference, that 60 kilometres per second difference, that if it's impacting on the speed of light, it would be detectable. You detect it by using what's called an interferometer, a Michelson interferometer, in fact. So these two guys did this experiment. They repeated it about 30 times over 20 years, I think, or something like that, and always got the same answer. The speed of light is invariant. Doesn't matter which way the Earth's going, doesn't matter what's happening, the speed of light is always 300,000 kilometres per second. And that then was built in to Einstein's special theory of relativity in 1905 that says that if the speed of light is constant, then time and space must vary. And that was proved almost immediately. And we've seen the proof of it many, many times since, that space and time can warp, but the speed of light is absolutely uniform. It's always the same. And the same is true when you go to general relativity. The speed of light comes into all that stuff as well. So the foundation of physics is that the speed of light is an invariant property. That's not to say people don't look for changes in it, but that's the basis of our understanding. And everything that we see in the universe supports that view. So as the universe expands, the speed doesn't change, but what happens is that the waves of light that are traveling through space get stretched, so they get redder. So that's where the idea of redshifts come from. The expanding universe basically draws out the light waves or the radio waves. It's the same no matter what electromagnetic radiation you're looking at. The wavelength gets longer as the universe expands, and so you get effectively a redshift. So, but the speed of light itself remains constant. Now, there is a very small body of opinion that has questioned whether at very, very great distances, in other words, at long look-back times in the universe, the speed of light was the same as it is now. And there's a group actually at the University of New South Wales led by I forgot his first name. That's ridiculous. Anyway, John Webb, Professor John Webb, who is he's a great guy actually. He's the sort of person when we used to be able to travel around the world, you'd go and visit an institution in Cambridge, UK, or in Tucson, Arizona, or somewhere like that. And John was always there, which is why it was always called the World Wide Web. I hope he doesn't mind me telling this story. But
I think that's right.
John is one of the few scientists who thinks he's seen evidence for something changing at these very great distances. What he does is he looks at the spectra of quasars, extremely distant quasars, and looks for things like I think it's called the fine constant. It's actually a constant of physics that you can try and detect in the light of very distant quasars. And he thinks he sees an effect. Most people think it's below the level of statistical significance, and that's why this is a slight set of lone voices coming out from people who are looking at this. But he thinks he detects something that could either be caused by a change in the charge on the electron, which is another fundamental constant, or a change in the speed of light. But I have to say, I think I'm correct in saying this anyway. It's a long time since I've connected with these people, but the mainstream view is still that the speed of light is invariant, that it was the same at the Big Bang as it is now and has never changed. But, people still look for changes. And the reason for that is because we believe that there is new physics that we don't know about, that sort of perhaps lies on top of relativity. Things that maybe would explain dark matter and dark energy. These are possibly new, what we would call new physics that's not dealt with by current quantum theory or relativity. So that's why people look for changes in the speed of light. But so far, I think it's true that it hasn't been detected. But a great question, Aaron. Thank you very much for asking that one.
Yes, indeed. So, Aaron, it's probably, or the popular opinion at the moment is it was probably 300,000 kilometres per second at the beginning, and it is now, and it will continue to be so until someone proves otherwise. And that's always the challenge in astronomy and space science and physics, is to find a different answer. And they're certainly doing that or trying to do that with the theory of relativity. So why not the theory of light as well? Let's move on to our next question. This one comes from the United Kingdom. Peter in Sheffield.
Hello, Space Nuts. This is Pete Ellinger from Sheffield, England. I have a question about remote sensing from satellites. How do scientists know the mineral makeup of the crust of the Moon or Mars when no geologist has been roaming around for years with their little hammer? Thanks very much. Love the show. Take care. Bye.
With their little hammer. I love that. They probably do take little hammers. They would have had little hammers on the Moon when, because I think in Apollo 17 there was a geologist, wasn't there?
Yes, that's
one of the astronauts was a geologist
with his hammer. And look,
yes.
Be careful what you're saying, Andrew, because Pete speaks like I did when I.
Yes, I know.
I had a little hammer when I were a kid and all. It's actually what's amusing is the electronic means that Hugh uses to turn the audio into text has made that into a little Hummer with a capital H, because it obviously thinks it's a vehicle that drives over the surface of the Moon or Mars. It still makes sense, but I know what Pete means. I know Pete means a little hammer, and that's what I'd say as well. Yeah, it's a great question, and actually, it does have links with Aaron's question a couple of minutes ago, because
I thought so. I kind of suspected we'd be going down that particular path about spectral analysis, I suppose, or spectrum analysis.
Yep, that's what it is. Exactly that, spectrum analysis. So it's such a rich field, this, and it's what allows astronomy and space science to work, because you can detect things at great distances from the makeup of stars themselves, because all the chemical elements in the atmosphere of a star put their fingerprint on the light that we receive from the star, and you can analyze that using a spectrograph, a device that breaks the light up into its rainbow spectrum colors, different wavelengths, sharp individually. And so that's how we know unequivocally what stars and galaxies are made of. And the same works for surfaces as well, because there you're looking at reflected light. So you've got the light of the sun, and if you pass that through a spectrometer or a spectrograph, that's the first thing you see is the light of the sun, or the spectrum of the sun. Sorry, the things we call absorption lines, which are the fingerprints of the elements in the sun's atmosphere. You know what that is because we've seen all that before. But then in addition to that, are features in the spectrum that comes from the surface that you're looking at, because they don't reflect light equally. That's the bottom line. The features that you see, and they're often, I should say, in the infrared spectrum, where you're looking at longer than redder than red light, effectively heat radiation. These features are often much broader than the spectrum features that you get from the elements in the atmosphere of a star, but they're still very well defined and very well understood. So what you do is you look at you've got a lump of calcite or something in the laboratory. Actually, calcite's a bad one because it's transparent. Let me think of something else. A lump of quartz, which is also slightly transparent, but don't worry. And you shine light on it and you look for what the spectrum response is. And then if you see that same spectrum response in remote sensing of a surface, whether it's on a satellite like Phobos or the moon, or on the surface of a planet, then you can tell it's the same thing. And there's a little bit more to it than that as well. There is a different signature that comes from vegetation. The chlorophyll in vegetation actually has a very strong spectral signature. So that's why, you can look at the surface of the Earth and know that it's got living organisms on it from space because you've got this strong spectral signature.
I remember some years ago you and I hosted a lecture once about perhaps using this kind of technique to look at exoplanets in the search for living organisms, and that was something that was being pioneered and certainly could be a great tool into the future when looking for plant life or some other kind of life.
That's right. These are, this is still a very, very active field of research, looking for biomarkers. What specific feature in the spectrum, say of an exoplanet or its atmosphere, what specific feature would be an unequivocal demonstration of the existence of biological processes? And it's actually not an easy thing to do. We thought we had it clinched about a decade ago with something called the vegetation red edge. And this is a spectrum feature that comes from vegetation. It's called the red edge because it actually is a drop in intensity in the spectrum. And but the trouble is that feature is reproduced by other features that have got no biological origin at all. So it's not unique. It's kind of gone off the boil a bit as the vegetation red edge. It is still produced by vegetation, and it's something people look for when they're doing earth sensing, because you can tell from the shape of the red edge whether that vegetation is alive or dead, for example. But it's not unique. There are other things that look a lot like it. I might just sidestep here because it is part of the same story, Andrew. You and I covered the news, I think in September last year, that phosphine had been detected in the atmosphere of Venus. And phosphine is a potential biomarker. The latest research on that, though, is pouring a little bit of cold water on it, because I read a paper yesterday that's suggesting that the phosphine feature wasn't phosphine. It was actually a sulfur dioxide feature in the atmosphere of Venus that was masquerading as a phosphine feature or being misinterpreted as. And so some of the excitement might have gone off that. We probably await a slightly more conclusive version of that research. But you see how basically it shows you how vital it is to have biomarkers that are absolutely unequivocal if you're going to start talking about life beyond the Earth. Phosphine's probably a biomarker on a rocky planet, but maybe that's not what was found.
No. I think you and I said at the time it'll probably turn out to be something quite innocent and natural, and definitely not Venusians. So, Pete, it's the analysis by of light that gives us the answers when we can't take our little hammers to these places. But they will take their little hammers there one day, I'm sure. Although it does prompt one question in my mind. Some time ago, or not, it was fairly recent actually, we talked about the what life might be like on other planets with different kinds of stars and how that might affect the way things evolve. we're just talking about how you shine a light on a piece of quartz on Earth, and then you look at the planets or moons or satellites beyond, and the same thing appears. Therefore, it's quartz. But would that be augmented or changed depending on the type of star that's shining on that rocky planet, for example, like a blue giant or a red dwarf or something like that? Would you have to allow for that, or could you make a mistake by thinking, oh, it's all the same as it is here, but it's not?
No, absolutely. You know, that's the first thing you do is subtract the light of the parent star from the spectrum, which is just standard procedure in this kind of analysis. So it's a good question, but it certainly makes a difference. If you've got the same material on a planet that's going around a very hot star as you've got on one going around a very cool star, a red dwarf, they will look quite different. But you could compensate for that by, as I said, you subtract the light of the planet. It's a technique which I've used myself in this sort of work.
There you go. All right. I knew Pete would probably have that as a follow-up question, so I saved him some work.
And while we're on, Andrew, there's absolutely nothing wrong with little hammers. They're grand.
Nothing at all. Nothing at all. In fact, they had the Winter Olympics at Littlehammer. Sorry, that was a terrible dad joke. Horrible.
Maybe it's time that we shut down for the week.
I think we should finish. Thank you, Pete. Thank you, Aaron, for your questions. And don't forget, if you have a question for us, go to our website, click on the AMA tab, and you can record it if you've got a device with a microphone. spacenutspodcast.com, of course. Click on the AMA tab. Or if you want to do it the old-fashioned way, just use our email interface and send us all the information. Either way, don't forget to tell us who you are and where you're from. Would be lovely to hear from you. And that does wrap it up. Fred, thank you for everything you do. We really love it, and it's very insightful as always.
A great pleasure. Thanks, Andrew. Thanks for having me, and we'll speak again soon.
We will indeed. Professor Fred Watson here on Space Nuts, and from me, Andrew Dunkley, and Hugh in the studio, it's goodbye from us, and we'll see you on the next edition. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.